Okay, let's take a look at another simple harmonic motion system. It's a torsion pendulum. Sounds like it's going to be more like a simple or a physical pendulum. It's actually got more in common with a spring mass system, and it is a true simple harmonic motion system, at least depending on what it is you're twisting. So we have some spring or a flexible rod, and I've attached a mass to it, in this case a disc, and if I rotate the disc a certain amount, the rod is bent and wants to go back to its original position, so if you let go, it'll oscillate back and forth like that. And if we were to measure the torque as a function of how much we rotated it, and this would be radians here, we would get a straight line, at least out to some point. Eventually you might break the thing, whatever it is. And the slope is kappa. Again, it looks a lot like K for a spring mass system, but this is torsion pendulum. So if we want to figure out what the equation is for the period of a torsion pendulum, again, think in general terms. On the equation sheet on the AP test, they give you the period is 2 pi square root of m over k. And when you see that, think inertia over the force constant, or the slope of a force displacement graph, or in this case, a torque angular displacement graph. You could call it, again, a torque constant if you want. And so the slope is the slope of the line is the torque constant, and the inertia is I because this thing is rotating. So it's 2 pi square root of I over k. Again, you should be able to derive this using this sort of general technique. You can also do it using torque equal I alpha like we did for physical pendulum. It is a good idea to have this in your calculator if you want, so you know what it is, but be prepared to show where it comes from. And so this is another way to show it. Torque equals I alpha, and so the torque is kappa theta. And so this is, again, the best fraternity to join, tau kappa theta. And alpha is omega squared theta, just like A is omega squared x for spring mass system. And so if we put this in for torque and this in for alpha, we get kappa theta is I omega squared theta, and thetas go, and you get omega is square root of kappa over I, and we know that's 2 pi over the period, so if you solve for the period, you'll get this. So two different ways of doing it. One, a sort of a graphical way of thinking about it, but once you derive what the torque is as a function of theta, you can come up with it. And so let's do a quick example. So we twisted a spring, so we didn't stretch it, we twisted it 100 radians, and it took 0.11 Newton meters to hold it. Find kappa, and so we're assuming 0, 0 is a point. Really, chances are if this was a free response, they'd give you a bunch of points of torque versus theta, and you do a graph and the best line fit. But this is a quick example, so we're just saying it's really the change in torque over the change in angle, and so this would be minus 0, and we get 0.0011 Newton meters per radian. And so we have a solid cylinder, we're going to hang from it, 0.027 meter radius, and we twist it some amount. It doesn't matter, right, because the amplitude doesn't affect the period in simple harmonic motion. And we release it, find the period, and so period is 2 pi square root of I over kappa, and I is 1/2 mr squared. No parallel axis theorem needed here. We're spinning it just about its center. It doesn't say anything different. I guess you could come up with a system that was somehow hung off center. I haven't ever seen that. It'd be hard to do, but you could definitely do it. That would be tricky, but so watch for that now that I've thought of it. But this is just about its center, and so we know the mass, we know the radius, we've already figured out kappa. We get 3.6 seconds, and then we did this in class. I had a spring in a cylinder that behaved this way, and it worked just fine.